In addition to understanding the size and overall structure of the galaxy, we're also interested in its constituents, what it's made out of. So that's something that we want to investigate as well. This view is what the galaxy might look like from an external point of view, which we'll never be able to get. But nevertheless, that should be pretty close. Well, just like obtaining its structure is hard, it's also hard to figure out what it's made out of. So the solution to our problem is that we can image the galaxy not just visibly, of course, but in many wavelengths and do 360-degree panoramas of this. And that should give us a pretty good story. So let's see some basic results of that. So looking at the Milky Way in a 360-degree panorama at various bands, the first one is the 21 centimeter radio emission from atomic hydrogen. So we see the various intensities at different regions. Of course, toward the center region, it's more prominent. The white shows more prominent emission of the 21 centimeter line based on the greater amount of gas in those directions. So this gives us a lot of information. Then we have radio emission from carbon monoxide. Of course, again, you detect carbon monoxide, you're detecting hydrogen gas. A lot of information there, revealing where the molecular clouds are. Very important information. Far infrared is associated with emission from interstellar dust. So we have relatively cool dust that's emitting infrared radiation, and that shows that distribution across the galaxy. Then the near infrared, closest thing to visible light. This is pretty interesting because you actually see the bulge in the disk. Real data associated with our Milky Way. The near infrared can penetrate through a lot of the dust that the visible light doesn't. Here's the most familiar one, the visible light emission. The Milky Way itself, as we have come to know it, if you're ever out in the dark skies in the country, you'll actually see this band. Probably not that prominent, but nevertheless it's there. Most of the light scattered and absorbed by dust. Then going down in wavelength, we have the X-ray. We see hot gas bubbles, X-ray binaries, producing hot spots in this spectrum. And the most energetic being gamma rays, primarily emissions from cosmic ray interaction with atomic nuclei. Together, all these different images at different wavelengths can be correlated with each other to give us a lot of information, like, for instance, the radio emission here. Well, radio emission is typically associated with cool dust. Sure enough, in the visible, there is a lot of cool dust that is obscuring our view of the light. In a similar way, we have far infrared. We notice something going on here. This would be associated with warmer dust, but then you kind of see that region in the visible there, but not punching through the dust that's associated with that region of the galaxy. So collectively, this gives us tremendous insight into the nature and the specificity of the constituents of the galaxy. Let's take another view in the near infrared, because in the near infrared we can actually see that bulge. So here's our galaxy, and there's the bulge. So this is a pretty interesting perspective. And considering that 360-degree panorama technique just mentioned, we really are in not the center of things, we're offset from the center, but the galaxy is wrapped around us. So we're essentially having to unwrap the data and flatten it out here so we can actually see what's going on a little bit. And it gives us a pretty good perspective of the view in the various bands. We've already come to realize that the center of the galaxy is not observable in the visible because only one photon out of a trillion gets through. But let's take a closer look in the infrared. So here we have the band of dust in the plane of the galaxy near the very center, Sagittarius. And as we magnify that a little bit, along with the associated gas that reveals itself in blobs here. A lot of interesting stuff going on. But as we take a closer view, we have very strong emissions coming from the very center itself. And that region, the Galactic Center, is an object known as Sagittarius A. So in the final image, which is a radio image, we'll magnify this tremendously. So we have 1 light year scale here. So this shows the stars, objects within 1 light year of Sagittarius A, which is pinpointed right there. There's a very interesting object right at that location, which is very dominant and very unique. And in fact, that very unique object turns out to be something that we have discovered in recent years. Only one solution for it, and that it is a black hole, based on a detailed and long-term investigation about the orbits of various stars, nearby stars, around this central object, Sagittarius A. As the details of that data have been researched, analyzed, it's been discovered that it needs to be a mass of about 4 million solar masses. And there is no other solution for any other type of object that we know about that could exist there. It couldn't be a whole bunch of stars. It couldn't be a bunch of neutron stars. They would coalesce into a black hole in any case. So there's a 4 million solar mass, supermassive black hole right in the center of our galaxy, producing tremendous speeds and dominating the central region of our galaxy. So that is evidence for the supermassive black hole in the center of our galaxy. Here we see an X-ray image, a Chandra X-ray image of Sagittarius A, the center of our galaxy, and it's going to look a lot different than a radio image. X-ray sources, of course, are very energetic, associated with black hole and neutron star binaries, so there's a lot of those in this region. Moreover, in recent times, we've seen a flare-up at the location where the supermassive black hole is, an X-ray flare-up. So even though it may not look all that impressive, nevertheless, it's something to take note of. In terms of the X-ray activity of the supermassive black hole, it's kind of a weakling in comparison to other galaxies. And there's a reason for that, for the relative low level of X-ray activity at our very center. And the most likely reason for that is simply that the available gas to fuel the consumption by the supermassive black hole resulting in X-ray emissions is basically used up. So mature galaxies would tend to be that way. Long ago, our Milky Way galaxy was likely much more active in the center, but the available resources to fuel it have been consumed. So distant galaxies, they're also younger galaxies based on how we're viewing them. It takes time for light to get here. They reveal greater activity than our galaxy does. Stars that make up the Milky Way have their own peculiar motions. There's essentially three different components. We have the halo stars, we have the bulge stars, and we have the disk stars, all doing different things. Let's focus on the disk stars for a minute. They're bobbing up and down like horses on a merry-go-round. The sun goes around in 230 million years, but it porpoises, the z-axis motion as it's called. The sun goes up and down with about a 33 million year period. So it actually passes through the disk of the galaxy every 33 million years. So it passes through different regions of stars. It doesn't do this with tremendous amplitude as some of the stars do, but nevertheless, this is a very interesting feature. Another interesting feature is that the inner and outer disk stars should be moving at greatly different speeds from each other, but the outer stars are moving a little bit faster than they ought to be, which we'll discuss momentarily. But this up and down motion is from the gravitational instabilities of the disk stars. So when our sun is, for instance, under the plane of the disk, it gets pulled up gravitationally, and when it's over, it gets pulled down, kind of like a swinging pendulum. Rather than stopping at the bottom of the swing, inertia takes it through and it goes up the other side, which accounts for the 1,000 light year thickness of the disk, this z-axis motion of the stars. The halo and bulge stars, in distinction to this, have random chaotic orbits. They're not nice, orderly, circular orbits, but more kind of like a bee's hive, a bee's nest, or a swarm of flies that are going in and out. So their history is also significantly different. Where the stars came from and how they formed is a different scenario than the disk stars. So I just mentioned that the outer stars of the Milky Way galaxy are going a little bit too fast. They should be going a lot slower than we detect them to be moving. This is a graph of orbital speed versus distance from the galactic center. Here's our sun with an orbital speed about here, and the stars that are closer in, you notice it's a little bit complicated. The reason being is that it's just not one, the galaxy is not one point mass at the center, whereas you go further out, you'd expect a very orderly Keplerian relationship between distance from the center and orbital speed. So it's a little more complex than that, but we understand it quite well. The material that's inside a given orbit is what produces the gravity to direct the speed of that orbit. The particular curve that we see here is okay for the inner region, but as we get further out, we should start to see more of a Keplerian orbit, where we have a definitive reduction in the orbital speed as we get further out. However, we have something that's very different than that, namely that the outer stars are actually speeding up, and we cannot detect the mass that would be associated with causing the orbital speed to be so large for these outer stars. So this is data that informs us that there's more than what meets the eye, that there's mass in the galaxy that can't be accounted for, that doesn't show itself in any normal way. And this is what is known as dark matter. So these galaxy rotation curves, what we just looked at, the orbital speed versus distance, informs us about additional mass that we need to account for. The matter in the disk and the halo can actually be determined based on those orbital characteristics. So there's really a lot more matter in the Milky Way than we can detect visually and in other ways, any form of electromagnetic observations can reveal. The total mass in the disk of the galaxy shows itself to be about 200 billion solar masses. And then in an extended halo, there's an additional approximately trillion solar masses. Now that's way beyond what we can detect. And just to clarify, the size of this extended halo is much larger than the halo I put on here, about 12 times the extent of the galaxy itself. So a smaller halo has the globular clusters and other stars in that component, but the extended halo of the Milky Way galaxy, about 1 trillion solar masses. Most of the mass isn't emitting any radiation, which provides the best evidence for the reality of some mysterious, exotic, non-electromagnetically emitting mass that's known as dark matter. And when we include this, it produces geometry, so to speak, of mass that provides agreement with the rotation curves that we just considered. So this dark matter is considered dark because we're in the dark, so to speak, as to what it is. And nobody's discovered that yet, and it's a big question in astrophysics and cosmology. It's because it seems like there's more dark matter in the universe than regular matter. So what is this mysterious stuff? We'll encounter that question again a little bit later. So the dark matter mystery is indeed a big mystery. It's distributed around the Milky Way in this huge halo, and it's about 90% of the galactic mass, currently unidentified, most of which is this mysterious dark matter, not regular matter that emits light. Now, small quantities, a little bit of this, can be accounted for by neutrinos, white dwarfs, but not a whole lot. And then there's other bodies as well, brown dwarfs, black holes, that is associated with regular matter. And so some of the unidentified matter is in that category as well. How much, it's not certain, but it's not a significant percentage of it. For instance, a brown dwarf coming along here can get in front of a distant star and actually gravitationally bend the light because of the warping of space and cause an enhanced light to be focused on the telescopes on Earth. Well, this type of event has been studied and discovered. These are known as massive compact halo objects, or MACHOs, and it accounts for some of this missing mass, but again, not very much. So we're still left with a big mystery pertaining to this reality of the dark matter. And now for a very brief and traditional explanation for the Milky Way galaxy and how it formed. So much is unknown about this. A lot of research going on to understand how the galaxies form in general. But we have a protogalactic cloud with hydrogen and helium, a little bit of rotation, and the halo and bulge stars are able to form in random pockets in this huge galactic cloud. So that produces the halo and bulge population of stars. Well, why did they seem so different than the disk stars? Well, that early formation doesn't use up all the gas. A lot of the gas is able to pass through those stars, and the physics will ensure that it will flatten out into a spinning disk as it passes through. So the old stars, the ones that are now the halo stars, are the Pop 2 stars, and the population 1 stars will be the disk stars. The lack of gas in the halo prevents ongoing star formation. The gas is passed through, so those stars get old and die in the halo. But the star-gas star cycle is supported and continues on in the disk. The disk has a high concentration of gas and dust that the halo stars don't have. And then over billions of years, we see only old stars in the halo. It's all that's left, but stars of all ages in the disk, because there's been multiple generations of stars being born, going supernova, seeding the interstellar medium with the heavies and producing new generations of stars like we see today. So that, in brief, is the history, and that will conclude our discussion of the Milky Way as well.